differential equations, or ODEs for short. And by the way, one requirement of this class is you do have to be able to read my handwriting. If something is unclear or the way I write it is unclear, just let me know, because sometimes, you know, my L's and my I's might look alike or something like that. So
you're better than Dr. Brian.
Okay, thanks. All right, so when you're working with an ordinary differential equation, and I guess the reason why I'm starting out with this is because it's a very good example of how we think a little bit differently in physics, is that the first thing you want to do is you want to be able to classify the differential equation. And there's two things we need to think about. There's a thing called order, and there's a thing called degree. And between the order and the degree of a differential equation, you can tell a little bit about how you're going to approach solving the differential equation, which is really what we really care about. You know, we don't care about the history of the differential equation. We don't care about a lot of the philosophy or theory behind it. We just want to solve it and move on. So, for example, let's suppose you have a differential equation where you're taking the third derivative of y with respect to x plus x square root dy dx plus x squared y equals 0. Okay? What happens with this equation is, in order to get the order and degree of the equation, first you have to rationalize the equation, which means you can't have a term with a radical. Okay? So, you know, we're not going to do it, but if you assume you square the equation and you rationalize it somehow, then the highest order term is going to be this third derivative term, but it's going to be squared. And because it's squared, this is going to be called a second degree equation. But it's also, because there's a third derivative here, this is a third order. So what this means then is that because it's a third order equation, that's going to affect one way that we solve it. If it was a second degree equation, we're going to solve that differently than we solve it if it was like a first degree equation. Okay? So this is going to kind of give you a hint into what your strategy is going to be. Now, to keep things simple, we're going to first start off with first order equations. And by the way, if you look at physics problems, just in general, you'll notice that most physics equations that we use to describe the physics in the world are usually no higher than second order. Occasionally you'll see third order equations where there might be a term dealing with friction or something like that. But most of the time it's not going to get higher than second order.
Square the first one?
Yeah, actually, yeah, it did, because this term was a radical. So because it was a radical, to rationalize it, we had to square this term. Okay. All right. So a first order equation is basically made where you just have dy dx. Okay. And most of the equations we're going to deal with here, they're going to be either first order or second order for most physics, but the degree could get higher than that. Now, for the homework, you might see some really nasty ones that get higher order, but that's just because, you know, this is where you guys are supposed to knock your heads against the wall to figure this stuff out. So let's see. So let's say we have this equation, ax dx plus by dy is equal to 0. Okay? So what happens here is that we can almost treat these derivatives as this is a fraction and just kind of break it up. This can also be written as dy dx is plus a of x over b of y equals 0. By just sort of dividing things through, you can see how that works out. And so what happens in this case is that you basically have the derivative of y with respect to x, and you have a function of x and a function of y. Okay? This is called a separable equation. And this is the easiest type of equation to solve, because all you really have to do is just integrate this equation where all of the x terms are here and all the y terms are here. So if you integrate this term with respect to x and this term with respect to y, you got your answer. And that's it. And so as the example they give in the book, they might have a of x is equal to 1 over square root of 1 minus x squared, and b of y is equal to 1 over square root of 1 minus y squared. And so what happens here is that you have essentially dx over square root of 1 minus x squared plus dy over 1 minus y squared equals 0. And so if you integrate, and this is where your Schoen's outline mathematical handbook comes into play, is that you just flip through the pages of that and you see that somewhere there's the integral dx over square root of 1 minus x squared. And according to the book, the solution to that is going to be inverse sine of x. So what we basically do is we integrate this term and we integrate that term, and we could also say we integrate 0. But when you integrate the first term, you're going to get inverse of x, and then say plus a constant. And you integrate the second term, and you get inverse sine of y plus some other constant. And that's going to add up to 0. So the net result is to say that, well, sine, inverse sine of x plus inverse sine of y is equal to a constant. And so that's your answer. Because the whole point here isn't to get the cleanest, nicest answer. It's really just to be able to get something without derivatives, where there's something of x and something of y, and there's no derivatives in between. And then you can call this a solved differential equation. Now you could take it further, and you could take the sign of both of these, and you use trig identities and everything else, and I think you'll get something like x square root of 1 minus y squared plus y square root of 1 minus x squared is equal to the sine of c, which is just equal to some other constant. And you could do something like that, and then you can keep working this until you have a nice, neat function. Y is this function of x. But that's all algebra. And we're doing differential equations here. We're not doing algebra. Okay. So the basic idea is that if you can do this, at least get it to, I'll put this in red. At least if you can get it to this point, you're done. Because if you can solve this part, then you're finished. You don't really have to worry about taking it too much further than that.
So you wouldn't expect us to do the algebra? Probably so. We've got a flat for.
Well, yeah. I mean, when you get to this point, you can say you're done and declare victory and move on. If it's something where the algebra is just not too hairy, or you just feel like doing it, you can just do it as a practice. But don't feel like you're obligated to get it into the algebraically cleanest possible form. And so what happens when you're really doing this in physics is that you want to get it solved, and then you want to get it in a form you can work with. So, like for example, if you're doing this to publish in a paper, and then you kind of want a cleaner form that people can read and they can understand it. But for the sake of your problem set, or your exam, then I would rather not have you spend a half an hour of your exam time trying to clean this up. I'd rather you spend that time working out the other problems, and then, and then you do it from there if you have time left. But the nice thing about it is, if, let's say, you could clean this up into a nice neat function of y as a function of x, then you could plug that back into the original equation here and see, does it still work? And you can test it. So that's the advantage of actually doing all the algebra, but if you're confident before that, then I'd say you don't need to worry about it. Okay. All right. Now, the next question then is, what if we use something like a of x and y dx plus b of x and y dy equals 0? So this is still a first order equation, but it's a little bit different because now it's not really separable because you have x and y terms all kind of mixed together. So you can't just integrate one of these and be done with it. The only way you could do that is if you could eliminate all the y terms from A and all the x terms from B. Okay? What happens here is basically that if you integrate the first one with respect to x, there's y terms in here, which could spoil the solution from working. And so what we're going to do is we're going to kind of assume that we have a solution u, which is a function of x and y, and it's equal to a constant c. Now, where this comes from is that partial u with respect to x dx plus partial u with respect to y dy should be equal to 0, right? And that's because, c is a constant, so you take the derivative of c, then you get 0. So when you take the derivative of u, then you do this whole derivatives with respect to each variable, like by a chain rule. Now, if you look at the similarity between the two equations, you could see that, therefore, A must be equal to partial u partial x, and B must be equal to partial u partial y. Now, also, we know from basic calculus that partial u, or second derivative of u with respect to both x and y, should be equal to both partial a with respect to y and partial b with respect to x. So we can use this because if partial a with respect to y happens to be equal to partial b with respect to x, then the solution is u is equal to c, and then all we have to do is find u. And we can find u because if this is the case, what that means is that we can just say, take the integral of a dx, and that should be equal to the integral of b dy, right? Except that here, the only thing we can't do, the only reason why I can't say that is because really, if I take the partial a with respect to x, then what this is going to give me is it's going to give me, sorry. Forget I got to get to a finer point. Then what happens is this is actually going to give me u of, or something like u of x and y, plus there'll be a constant term where this constant term is going to be a function of y. And the reason why is because if I take the derivative of u with respect to x, then the constant with respect to y kind of falls off. And meanwhile, I'll do the same thing with b, and I'm going to get some other u of x and y, and then a constant with respect to x. And if these two are equal to each other somehow, that's when I got my solution. Actually, I'll call this u bar. I don't want to use the prime because I can get confused. So let's do an example with this. Let's say, for example, we've got x plus y dx plus x dy is equal to 0. In this case, we have a is equal to x plus y. And we have b is equal to x. Okay? So now the partial of a with respect to y is equal to 1. Partial of b with respect to x is also equal to 1. So because of this, we say this is exact. And so the if you take the integral of a, so that's x plus y with respect to x, then you get 1/2 x squared plus xy, plus there's a possibility there's some other function of y out there. We don't know. If you take the integral of x dy, then that gives you x times y plus maybe there's some other function of x. Now, are these two equal to each other? Yes, no, vote, anybody? Yep. Yeah, they are. And the reason why is because this function of x could be equal to this. All we know is it's a function of x only. This function of y here is just 0 because there's no equivalent down here. So therefore, we could say that our solution u of x and y is equal to 1/2 x squared plus xy is equal to c. Okay? And so that's how, if it's exact. So just reviewing real quick, there's two things. There is it separable? then you could just do the straight integration. If it's exact, then you got to do this little test, and if it passes the exact test, then you could just do the integration of both and compare, and you're done. So using these two, you can solve, I'd say, at least half of the first order, first degree partial, ordinary differential equation problems. Okay. All right, any questions so far? As we go on, we're going to get into more and more complicated cases.
So you assume that they may be equal, and in order to prove these that these
Well, we know that if it passes this test, if partial A with respect to y equals partial B with respect to x, then it must be exact. And if it's exact, then we can do this, and we're confident this is the answer. So basically, it's not random. It's basically like, we kind of have almost imagine a flow chart in your mind where you look at the problem and you say, this is a first order, first degree problem, okay? And if it's first order and first degree, then the first thing you should think of is it separable? Can I separate all the x terms and the y terms from each other and just integrate it? If you can do that, you do it and you're done. If the answer is no, then you go to the next step in the flow chart. Is it exact? And I test if it's exact by doing a little trick and take the a and the b term and I take derivatives and I see if they're equal to each other. If the answer is yes, then I do these integrals and I'm done. If the answer is no, then we move on to the next one. And the next one is where we use an integrating factor. And the basic idea is that if you have this function lambda of x and y of a dx plus b dy is exact. But a dx plus b dy is not exact. So in other words, you got a situation where if you could only had this extra term, then it would become exact. So what we do is this term right here is called an integrating factor. And so it's something that we're going to throw in to the problem in order to make it exact. And then once we made it exact, then we go back and use the other stuff. So what we do here is assume that you have an equation dy dx plus f of x y is equal to g of x. Okay? Well, let's suppose I multiply this whole thing by a term lambda. Okay? And in this case, I'm just going to use lambda of x. So I have lambda of x is equal to dy plus f of x y dx. And then this is all going to be equal to g of x dx with the multiplication by lambda of x. Okay? So this is the equation I have right now. Now, what happens is you can integrate the right-hand side easily, because the integral of lambda of x, g of x, dx is known. Okay, everybody know why it's known? Because it's just x's. There's no y's. So all we have to do is just throw it in. If we know what if we know what lambda of x is, if we know what g of x is, we can integrate. We can integrate anything, any function out there that can be written. We know how to integrate. Just assume that. And the reason why is because we have Shelm's outline. So this is known. Now the left-hand side here, if we can integrate the right-hand side, then whatever the integral of the left-hand side is going to be equal to that, right? And so you'll notice here that if the left-hand side is exact, okay, then all of this is basically going to be equal to partial u partial x or partial u partial y. And so if we assume that in this case a of x and y is equal to lambda of x f of x y, and b of x and y is just lambda of x y, right? Then partial a with respect to y is just going to be equal to lambda of x f of x. Partial of b with respect to x is going to be equal to the derivative of lambda with respect to x. And, oh, sorry, that was, there's no y here for the b term. Sorry, I got a little overzealous there. That was a dy, so I don't have that. So if these two are exact, then therefore we see that partial lambda with respect to x is equal to lambda of x f of x. Okay? Now, this is now a differential equation inside a differential equation. But we know how to solve this, right? We know how to solve it because the solution for this is just simply going to be lambda of x is equal to e times the integral of f of x dx. If you take a derivative of this lambda term, then what happens is the term in the exponential kind of gets spit out, and you end up getting the derivative of the term in the exponential, which is just f of x. And that is being multiplied by e to the integral, or e to the term with the integral of f of x, and that's just going to give you a lambda term there. So therefore, you could see that the derivative of that this thing has got a hole. So it's exact, and the integrating factor, as long as the integrating factor is equal to this, then it's exact, and it works. So what we just did was we found the integrating factor that works if your equation happens to be in this form. And so anytime you can put your differential equation in this particular form, you know the integrating factor, you multiply by that integrating factor, it becomes exact, and you can solve it using the other methods.
For the so we have d lambda, we end up with the result of d lambda over dx equals to lambda x as a function of that.
Right.
How do you go about that? How do you have
well, because I said this is a and this is b, right? When you take the derivative of a with respect to y, you lose the y. So you just get lambda x f of x. And then for b, you take the derivative with respect to x, which just gives you the derivative of this term. And you just set those two equal to each other, and that's how we got the differential equation. So then once you solve it, you know, you basically have a function or a solution for lambda of x. So then all we have to do is we just solve for whatever that integrating factor is. So let's do some examples. So let's say we have x, and then I'm going to be lazy and just write this as y prime plus 1 plus x y is equal to ex. Okay? Now this fits the form that we talked about before if we divide through by x. So now we have y prime plus 1 plus x over x, y equals ex over x. And so what happens is you could see that we have the dy term by itself. Our f of x is all this stuff. So it's equal to 1 plus x over x. And then our g of x term is equal to e to the x over x. Okay? So what's happened now is that in order to get lambda, we just have to solve for lambda of x is equal to the exponential integral of f of x dx. And so that is equal to e, and then we have an integral of 1 plus x over x dx. And when you integrate this thing, I'm just going to say long story short here, it's equal to x e to the x.
On a test, is it okay to, from the last page you filled in all the filler, like y, lambda is equal to that. Is it okay if we basically write this down?
Yes.
Solution, or do you want the filler stuff?
Well, no, you don't have to solve for what lambda is. You already you could basically start out with you have this function lambda of x, you know what that is, and then for something like this, at least on the midterm, you know, you're going to go to your Shalom's outline and use that to solve this integral and simplify your exponential. So no, you don't have to derive the integrating factor every single time. All right, so now you got your integrating factor. Now you can multiply this thing through. So you're going to have x e to the x, and then you have y prime plus 1 plus x over x y is equal to e to the I guess this would be e to the 2x because we have x and then 1 over x, so it works out. Now what you have to do is you have to integrate both sides. So the integral of x e to the x dy is going to give you this first term. And then this is supposed to be equal to the integral of x e to the x times 1 plus x over x y dx. And that in turn is going to be equal to the integral of e to the 2x dx. Okay? So you have to solve all three of these integrals. And when you solve the three integrals and you set them equal to each other, that should give you your answer. So the first one is pretty easy. You just have x e to the x y, right? Because there's no other y's involved. The second one is going to take a couple steps. So we can simplify this down to e to the x times 1 plus xy dx. The last term is just going to be equal to 1/2 e to the 2x plus c. And so for this middle term, you can expand this out and say now you have e to the x y dx is one integral, plus you could have a second integral, which is going to be like x e to the x y dx. And when you take this first integral, it's just going to be essentially just going to be e to the x, right? Because e to the x, when you take a derivative, it just becomes itself. So you just have an e to the x times y. The second one here, you've got to think almost in terms of a chain rule, but you can also look at your Shom's outline on this. And so what this comes out is like x e to the x minus e to the x, all times y. And so this term right here cancels out with this term. And so this middle term you're just left with is just going to be x e to the x y, which is exactly the same as this one. So that looks pretty good. So the net result here is going to be you have x e to the x y is equal to 1/2 e to the 2x plus c. And by the way, number one problem I've seen people have when they're solving these ODEs is they leave off the constant. If you don't have the constant, then you kind of get into trouble because you can't. You'll miss terms that you need, and it'll cause problems later on. And then if you want to do a little algebra here, since you are pretty much already there, you can just divide everything through by this x e to the x, and you have a neat function of y of x. And see, if you lose the constant, then you don't get this last term, and things don't quite work out right.
You substitute dy?
What?
You substitute dy to be integrated?
Yeah. Yeah. And so the neat thing is, like, once you got to this point, if you wanted to, you could always take the derivative of this term and just see if you recover everything else. Because if you do everything right, then if you take partial y, partial x of this, it should give you back e to the x over x minus 1 plus x over xy. So it'll just be a matter of, doing the derivative and then just seeing if you could somehow squeeze this out. And of course, you have to know that y is equal to this stuff. So plug that into y and you'll have the answer. So anyway, like I said, that's if you do the algebra, it's got the advantage of having a self-check. Otherwise, just if you can't, then just be confident you're hopefully doing it right. All right. The next method I want to talk about is I call this the try method, and you'll see why. So let's suppose you have y dx plus 2 square root of xy minus x is dy is equal to 0. Okay? So the reason I call this a try method is that if you look at this, this is not separable, obviously, because you have x's and y's all mixed together over here. It's also, it doesn't look like it's exact either, because if you take a derivative of this with respect to y and this respect to x, it doesn't look the same. So what we're going to do is we're going to try a substitution. In this case, I'm going to say y is equal to vx. And what I try, it's sort of a random choice, but it's also one of these things where when you've worked out enough problems, you might, your intuition kind of gets a little bit better. And you can try the right substitution and get you the right answer faster. So you try this substitution where y is equal to vx and dy is equal to v dx plus x dv. And then if you substitute this into the equation, so we're eliminating y in favor of a new variable v, then we have vx dx plus 2 square root of xy, or sorry, x, messed up here. 2, it should be xv, x square root of v. Minus x. And then for the dy, now you have v dx plus x dv. All this is equal to 0. So what happens, you can take this and now simplify it by just multiplying all these terms out. Then you have 2v to the 3 halves dx plus 2 square root of v minus 1 x dv is equal to 0. Okay, now that you've done a substitution, is this separable? Yes, no? Well, what if you just divide by x and then divide by v to the 3 halves? Yeah. What about this? Is this separable? Yeah. Okay. So like I said, it's just a simple algebra move from there. And then you can see it's separable. And if it's separable, then you could just integrate the thing and you're done. And even if it wasn't separable, we could try to make it exact. If we could, you know, get it at least into a form, we could use an integrating factor or something like that. And so another example is, let's suppose we have x y squared times 3y dx plus x dy minus 2y dx minus x dy equals 0. Okay, so now I'm going to try v is equal to y squared x, and that means that x is equal to v over y squared, and dx is equal to dv over y squared minus 2v dy y cubed. So if I make this substitution, I can get this thing down to a form where I have 3v minus 2 times y dv, and then I have plus 5v 1 minus v dy equals 0. Is this separable? Yes. Because I could just take all these terms involving the v, divide them through, divide them through here and divide the y term. I got my y's and my v's separated, and I'm done. So really, the only reason why this is separable here is because the right-hand side is 0. If I didn't have a 0 right-hand side, it may not be separable. So what you're going to do so far is you look at your differential equation. You try to ask yourself, is it separable? Is there anything I could do algebraically to separate the two variables, the x and the y? If you can, it's separable, you just integrate. If you can't, then you move on to, is it exact? And exact basically means you do that little test with the a's and the b's and see if they work. If that works, you can integrate the two parts, you're done. If not, you think, can I put it in a form where I can either make it separable or exact? Where I use an integrating factor, or I can make it separable. And that's basically the substitution or try method. So those are essentially the 3 different ways, or 4 different ways, however you want to look at it, of how you can attack a first order ODE, like first order, first degree ODE. So all of those you ever see, you should be able to solve. Okay. All right, any questions so far? Anybody want to take a 5-10 minute break? Okay. All right. You guys want to take a little break, and then after the break, we'll talk about second order ODEs and other fun stuff. Yeah.
This one I've seen. Where did you get this one?
Oh, the dy?
Yeah.
Oh, that comes from taking this y prime, which is dy dx, and dividing it out.
Okay. I see it. Thank you.
Jeez.
Control release form, is that okay?
Yeah, that's fine. Yeah, I think I signed that, so it should be good. Man. I've gotten 30 emails in the last hour.
That's the reason to see before and then or yeah.
If there's a big big deal, you should take the first of the class.
I do is good, but like for experience, I never started to like after the first week for me. But like you can come when you're out there, it's like the night level that it makes you able to when you're down level to do it. Yes, first one's 4, and I think in my class is 4.
You might want to stand up, stand in the back.
Oh, yeah, that's fine. Yeah. Late date.
Yeah. Probably not strict to the deadline to take the exam. Yeah.
All right. So, is anybody here looking for a TA or interested in one? Probably wouldn't be good, but because it is supposed to be a 20-hour-a-week commitment. Yeah, you got to sleep sometime. So, anyway, just throwing that out there so anybody can think about it if they're interested. Otherwise, also, one thing we are doing differently this year is we have 1 credit hour elective courses to take, you guys can take. So if anybody is like a full-time grad student or, you need 1 more credit hour, we have classes you can pick from for that. I'm teaching one in the spring, and those are meant to be a lighter time commitment than the full elective. So it'll be just 1 hour a week of meeting and appropriate amount of homework going with that. All right. So let's get started again. Oh. Okay, so next thing I want to talk about is second order ODEs. We already talked about first order. And essentially, there's a big difference here, and a lot of the techniques you use, like separable and things like that, you can't really use with a second order ODE. But there are a few different things you can do to try to solve them. One trick, which I'm not going to go into, well, I guess I can go into a little bit later, but there are ways to turn a second order ODE into a first order, and then you can use all those tricks. But otherwise, you mostly are going to solve it using a substitution method, or you can do expansions and try to use those. So I'm mostly going to focus on the examples here. So this is a second derivative of y with respect to x, plus 3y prime plus 2y is equal to ex. Okay, so this is a typical second order ODE that you might run into. And the idea here is that you want to make some kind of substitution, and you're basically going to try a solution. And if you're right, then you will pretty much solve the problem or turn it into an algebraic problem you can solve. Now, what I do with something like this is my attempt is going to come from a clue in how the problem is structured. In this case, you see the exponential term on the right-hand side. And then you also notice that you have y double prime, y prime, and y. So we have the same order of derivative in y, or sorry, a same degree in each one of these. So in other words, if these guys were all to cancel out, let's say we didn't have the e to the x on the right-hand side, then what would happen is you would say that somehow y double prime and y prime are equivalent as far as the power of x. So we're going to try y equals e to the mx as a solution. And the reason why is because when you take y prime, that's going to be basically m times y, right? And y double prime is going to be equal to m squared y. So in each one of these cases, they're all basically a multiple of y. And now when I take this and I plug it back into the equation, I get m squared plus 3m plus 2. All of these are being multiplied by y is equal to e to the x divided by y. I just divided the y through because these are all multiplied by y. Now, what we do is when you're dealing with a second order or higher ODE, you've got two parts. There's a part of it is called the complementary solution. And the other one is called the particular solution. And the complementary solution is basically the same thing, but you put a 0 on the right-hand side. So you've got m squared plus 3m plus 2 equals 0 is the complementary solution. And so when you solve this, what this is going to give you is the solution for y, which doesn't contribute anything to the right-hand side. And then you've got another solution from here, which is going to contribute something to the right-hand side. Now, the problem that you run into here is, okay, is there a value of m which you can solve here that is going to give you 0? No. Nobody can think of anything? Okay. So, I mean, finding a single value of m that works is kind of troublesome. But even more so over here is that if m is not equal to 1, this is going to give you trouble on the with the particular solution. And so if m is equal to 1, that means m must be equal to 1. And then you have basically a 1 on the right-hand side, which means that this is going to be m squared 3m plus 1. And now m must be equal to 1, and that doesn't add up either, right? So this is in trouble. So what we learned from this is that this attempt I made here As great as it was, it just isn't going to cut it. So this is what we call a failed attempt. Yeah. So now let's try something different. Let's try a more complicated solution. And that's going to be y is equal to a e to the x plus c1 e to the minus x plus c2 e to the minus 2x. And the reason why I got that was because, it's complicated, but from this complementary solution, we know that we can reduce that down to m plus 1 times m plus 2 is equal to 0, right? In which case, you get two solutions here. M is equal to minus 1, and m is equal to minus 2. And either one of those solutions satisfies a complementary solution, but neither one satisfies the solution over here because of the fact that you need a term that's like e to the x in order for this to work. So the full solution that we're going to try here is essentially the sum of the complementary solution and the particular solution. That makes sense to everybody? So what we can do once we have this is we calculate y prime, which is just a e to the x minus c1 e to the minus x minus 2c2 e to the minus 2x. And we have y double prime, which is a e to the x plus c1 e to the minus x plus 4 c2 e to the minus 2x. Okay, so this gave us m equals minus 1 minus 2. So now if we take this and we plug it back into the original equation, what we get is our y double prime plus 3y prime plus 2y should be equal to taking this first terms, a e to the x plus c1 e to the minus x plus 4 c2 e to the minus 2x. And then I'm going to add to that 3a e to the x minus 3c1 e to the minus x minus 6c2 e to the minus 2x. And then I'm going to add to that 2 times y, which is 2a e to the x, plus 2c1 e to the minus x, plus 2c2 e to the minus 2x. And the result, you can just add straight down vertically here, is you get 6a e to the x, and then you have 1 minus 3 plus 2 is 0, right? And then 4 minus 6 plus 2 is 0. And this is all supposed to be equal to e to the x. So therefore, a must be equal to 1/6. And so if a is equal to 1/6, then you can go back to your original solution here, and you'll see that y must be equal to 1/6 e to the x plus c1 e to the minus x plus c2 e to the minus 2x. Okay? So what I did here was I saw my problem, and I first assumed that the solution had a form like e to the mx. Okay, I used that to come up with a more detailed problem, but when I plugged this in to the complementary, complementary solution, I found values of m that work, and I found 2 of them. But I knew that neither one of these was going to give me the e to the x on the other side. So I tried a new solution where I had both the complementary solutions, which will give me 0 and not contribute anything to the right-hand side, and another solution which is designed to give me something like an e to the x on the right-hand side. And then I took all the derivatives, plugged it back in, and found out what my missing term was. Now you notice you can't determine C1 and C2 exactly here, because C1 and C2 are, they could be anything. So they're not necessarily, they're not necessarily 0, but they're not also necessarily another particular number. Does that make sense? So these two are indeterminate, and no matter what number you put in there, you're still going to get 0 on the right-hand side. This term has to be 1/6 if this is going to work. And so by doing that, we found a solution to the differential equation. Let's see another example. And remember, the trick here was we didn't just find the particular solution that worked. We had to find the complementary solution and add that in order to get the full solution. Now another example is x squared y double prime minus 2y equals x. All right, so now the complementary function is going to be x squared y double prime minus 2y equals 0. Now, just from a strategy point of view, for people who want to pass, it's best to figure out your complementary solution, even if you can't solve this other one, because this is half credit, and you need partial credit to survive. And so, even if you can't solve this problem, solve the complementary solution. At least you got half the problem right. So for this, I'm going to try y is equal to x to the m. Okay. Now, why did I choose that? Any ideas?
Because of the x squared of that?
Right. Exactly. Because what happens here is that when I take something like x to the m, when I take a derivative, I lose a power of m up here. And so I've lost 2 powers of m when I take a second derivative. But somehow, when I multiply this by an x squared, they're the same, and they can cancel out to give me 0. So therefore, I want x to the m so that I keep the same power of x overall. Now I take this, I plug it in the solution. I know y double prime, or say y, I'm just going to do simple. Y prime is going to give me m x to the m minus 1. Y double prime is going to be m times m minus 1 x to the m minus 2. So when I take this and I plug it back into the complementary function, I have essentially m times m minus 1 x to the m minus 2 x to the m equals 0. Now the x to the m's are the same, so I can ignore those, and I just have m times m minus 1 minus 2 equals 0. Now to solve this, what I would do is I would multiply this out, so I have an m squared minus m minus 2 equals 0, and then I would factor it. And I can get, let's see, this should be an m something 1 times an m something 2, right? And I'm going to say the minus sign should be on the 2 because when I add it to the other one, it gives me negative 1. And so that's how I factored it. And so therefore, I have m is equal to either 2 or negative 1. And that's the complementary solution. So that means that I have a complementary function, y is equal to c1 x squared plus c2 x to the minus 1. All right, so that's half the problem right now. Now to get the other half, let's suppose, well, I know that I'm going to have to end up with an x on the right-hand side, right? And let's suppose that I don't know what I can guess as a form of y that's going to give me that. What I'm going to do is I'm going to do sort of a searching method of doing that. And what this is I'm going to take C1 and I'm going to replace it with U1, which is a function of x. And I'm going to take C2 and I'm going to replace it with U2, which is a function of x. Okay? If I do that, then y, I could say, is equal to U1 of x, x squared, plus U2 of x, x to the minus 1. And the idea being that since these are both functions of x, that if I plug this back into the other differential equation and solve it, where I have a non-zero right-hand side, what will come out is that I'll have the right function of U1 and U2 in order to make this work. And if U1 and U2 were just constants, then I got the complementary solution. So this is just sort of a different way of going about it rather than trying to guess what the other term should be. So now y prime is equal to 2xu1 minus 1 over x squared u2 plus x squared u1 prime plus 1 over x u2 prime. Okay, now I do not want to have higher order terms. I don't want to have like u double primes anywhere or anything like that. So what I'm going to do is I'm going to assume that x squared u1 prime plus 1 over x u2 prime is equal to 0. That gets rid of this stuff right here. And therefore, I have now y prime is equal to 2x u1 minus 1 over x squared u2. Okay, now when I made that assumption, this is just something to keep in mind. What I did was I inadvertently added a second differential equation that we're going to have to deal with later on. So that's kind of the drawback, is that this thing, when you make an assumption, it doesn't mean that things magically go away. It means that this is still something we're going to have to deal with. So now y double prime is going to be the derivative of this, so it's going to be 2u1 plus 2 over x cubed u2 plus 2xu1 prime minus 1 over x squared u2 prime. Now, I don't want this second term to go away because, first off, if it went away, then I would just be back to the complementary solution. And secondly, I don't want to add another differential equation I'm going to have to deal with later. So what happens is you can take this solution, you can plug it back in the original differential equation, and you get x squared times this. So it's 2x squared u1 plus 2 over x u2 plus 2x cubed u1 prime minus, this is just u2 prime. And then I am going to take this and I'm going to subtract 2y off of it. So I have this minus 2 times y prime, so that's 2u1 x squared minus 2u2 over x. And the result of that is going to be just equal to x. Now, here's the thing. This term and this term are the same. This term and this term are the same. So I'm left with 2x cubed u1 prime minus u2 is equal to x. And then also I have a second differential equation, x squared u1 prime plus 1 over x u2 prime equals 0. So this would be prime. So I have these two differential equations. Okay? Now, you can think of these as two differential equations, or you can think of them as two equations and two unknowns. Whichever one is easier to think about, right? Because now, it's a good thing I have this extra equation laying around. Now, instead of having to worry about solving this differential equation, I can just solve for the unknown. So what I do is if I multiply this bottom equation by x, for example, now I have x cubed u1 prime plus u2 prime. And then I add these two equations together, and I end up with something like 3x cubed u1 prime is equal to x, and the other term just drops out. And so that gives me u1 prime is equal to 1 over 3x squared. And then if I did something similar with the other equation, just multiply, instead of adding these two together, let's say I multiplied by 2 and subtracted, then I could get something like u2 prime is equal to minus x over 3. You have to think about the algebra a little bit to make that work. And so now I have u1 prime and u2 prime, and they're separate. So I could just integrate them. So I have u1 is equal to 1 over 3x with a minus sign plus c1. And then I have u2 is equal to minus x squared over 6 plus c2. And then my y, which was just equal to taking u1 x squared plus u2 divided by x, is going to be minus 1/3 x plus C1 x squared minus 1/6 x plus 1 over x C2. And now we can combine the terms of the same power of x, and we're left with minus 1/2 x plus C1 x squared plus C2 over x. And you notice that these last two terms are exactly like our complementary solution. So this is sort of like a brute force way of going about solving for what the particular solution is, assuming that you just couldn't guess and figure it out from there. And then you can always take this solution and take the derivatives and plug it back in and make sure you get the x on the other side. But it makes sense that this would work because, after all, you got the x term here, and there's an x that shows up over here, and the y that just carries right over from the line. And if you take a second derivative of this term, you get 0, so it makes sense it works, right? Very logical. All right, we only got 2 more things we got to do today, and then we're done. And so we'll probably be out of here within the next half an hour. The first thing is talk about power series solutions. Okay, this is essentially how I think Mathematica works, although I'm not 100% sure. And the basic idea is if you're not very creative, which you have to be in order to make all these assumptions and, like, to try a particular solution, then you can get around creativity by using brute force, and that's what a computer would use. So let's suppose that this is your differential equation, and it's a second order equation, so none of that separable or anything like that. So we're not even going to try a solution. We're just going to do a brute force method of solving it. And what that means is that you're going to try a power series. Because one thing you're going to learn next week is that any function can basically be expanded out as a power series, essentially, an infinite series of terms. And the only question is, are you willing to calculate out enough terms to solve it? And if you're most people, the answer is no. But any function can be broken up like this. And so what I think Mathematica does is it takes this power series where you don't know what these coefficients are, and then it takes the derivatives of these. So you take the second derivative, and then you plug the second derivative back into this equation. So you end up with something like 2c2 plus 6c3 plus 12c4, etc. And this one is going to be an x, and this is going to be like an x squared, etc. And this is going to be equal to x minus the entire infinite series again. So C0 minus C1 x minus C2 x squared, etc. Okay? And let's say you're a computer and you can go out to like a few hundred terms doing this. Now, what you do is you equate the powers of x that are the same. And so you see, like, for example, there's no power of x here and there's no power of x here. So we have C2 must be equal to minus 1/2 C0. And then we have C3 must be equal to 1/6 minus 1/3 C0 C1. Because you have a power of x here, and a power of x here. And C4 must be equal to minus 1/12 C1 squared plus 1/12 C0 cubed. And so basically, every coefficient can be written as some kind of function of C0 and C1. And so if you know what C0 and C1 are, you can define the entire series. And once you've defined what all the coefficients are, then you can essentially find the function that fits that series, and that's your solution. So that's so what we would have to do as humans is we need to know what C0 and C1 are. So we're going to have boundary conditions out here. So for example, we want y to be equal to 0 at 0, or at x equals 0, and we want y prime to be equal to 1. So this is at x equals 0. So if that's the case, then C0 must be equal to 0, and C1 must be equal to 1. And if C0 and C1 is 1, then you can use that to populate everything else. So you have C2 is equal to 0, C3 must be equal to 1/6, C4 must be equal to 1/12 or minus 1/12, etc. So you can figure out every single term from there on out. Now the problem with that is, like I said, it's computationally it's going to be very expensive to get enough terms to actually figure the whole thing out. So it's very, very tedious. But if you're a computer, then this works. Otherwise, if you really, really get into a bind, you can still use this method if you can't figure anything else. Now, what we would do in general is we might have something like the nth derivative of y with respect to x plus a function n minus 1 of x d n minus 1 derivative of y with respect to x and then this is an infinite series going all the way down to f0 of x, y equals 0. And so what happens is near x equals 0, the equation is finite and it's real. So we have some x equals 0 that's important. And the solution is going to be a Taylor series, which is basically written like this. And so this basically gives you a solution which is accurate around some solution x equals 0. So it's giving you a partial solution to, within a certain range that you might be susceptible to whatever you're doing. Now, what you can do is you can substitute that back into the ODE, and what happens is if you get something that is infinite or imaginary, then you might have a solution that looks like y equals the sum. Sorry, got ahead of myself. you might have something like y equals x minus x naught s as a sum from m equals 0 to infinity of Cm x minus x naught m, where C naught is not 0. And so basically what this does is it kind of subtracts out the singularities so that you end up getting a reasonable solution. And then there's approximation methods, and where the one approximation method I do want to talk about, I'm not going to talk about this graphical method, is the Wkb approximation, which is on the last page of the notes. And Wkb approximation is actually something that you might hear about in, it's used in physics a lot, I guess, especially if you're doing like perturbative methods and quantum mechanics or something like that. And what I'm going to do here is not going to be the complete Wkb approximation. They go into a lot more detail on this in the book, but I'm just going to try to give you like a flavor of how it works. And the reason why is because you need to know, I guess, when you're using these methods, you need to know more about them, but we're not focusing on them a lot in the class. So let's suppose you have a differential equation that looks like this. Okay. Now this almost looks like our general form of our integrating factor problem. The only difference is this is second order, so you can't use an integrating factor here. And you're going to assume f of x is some function that varies very slowly, so it's almost a constant, but not really. Then what we can do is we say this is going to be some very slowly varying function. So what we're going to do is we say if f of x was constant, then life is easy, right? Because now this is a very simple equation to solve. And if this is constant, then y would be approximately equal to e to the I phi of x, where you could say that phi prime squared plus I phi double prime plus f is equal to 0. So in other words, if f of x was a constant, then you could assume that if you take the second derivative of y, then you get something like negative y, and the phi is there just to give you something where it's not exactly just negative y that pops out. It's just meant so that when you take this second derivative terms, or these terms that fall out when you take the first and second derivative, it gives you this f back. Does that make sense? So in doing that, you're going to, this is something that approximately comes out. Then if you take phi double prime to be small, then what happens is you don't have to worry about this term very much. Okay? And you now have phi prime and f which relate to each other. And so you can see that phi prime is approximately equal to plus or minus square root of f. Now, if that's the case, then phi should just be equal to plus or minus the integral of square root of f dx. Now phi double prime, the magnitude of that should be something like 1/2 the magnitude of f prime over square root of f, and that should be really small compared to f, which in turn means it's really small compared to phi prime. Okay, so what we can do now is, instead of saying, well, we kind of assumed here when we said it was small, we assumed it's 0, and then found a better solution for it. What we were able to do now is we could say, well, phi double prime is really equal to plus or minus 1/2 1 over square root of f times f prime. And so this is known as the second approximation. So in other words, in order to do these WKB method, it's called an approximation method for solving a differential equation, where you're just kind of making assumptions and then following those assumptions in order to get something a little bit more precise. And then over time, you get something where you know it's not an exact solution, but it should at least look like an exact solution or feel closer to it. But you start building your way back up. So the first approximation was basically that f of x was constant and giving you this. The second approximation is that your phi double prime is equal to this. Now, if phi double prime is equal to that, you can do an integral of it, and you can see that phi prime should be equal to f plus I over 2 f prime over square root of f. Or sorry, that should be squared. And that just comes from, this equation again. And then that means that phi prime is approximately equal to plus or minus square root of f plus I over 4 f prime over f. And then once you have phi prime, you can use that to solve for phi. And we can say phi is approximately equal to plus or minus the integral of all this other stuff. Okay, and then once you have phi, now you can solve for f again, or sorry, y. So y of x is equal to 1 over f of x, the 1/4 power. And then you're going to have this as c plus exponential I integral square root of f of x dx plus c minus exponential of minus I integral square root of f x dx. And then I think that's it. That's right, close brackets. So the reason why they call this a Wkb approximation is because the Wkb functions are this f of x to be minus 1/4 times the exponential terms. And these are integrated from x0 to x of square root of f of x dx. And so these are known as either w plus or minus. And so therefore you could say that y of x is approximately equal to alpha plus of x times w plus x plus alpha minus of x, w minus of x. And so you can use this in order to kind of form a approximation of the solution. Okay, so anyway, I just want to sketch out how you do that. And this works if you're dealing with something very nonlinear. I'm a little biased because, you know, in my area, I'm doing computational physics. Instead of going through this method, I would probably just have the computer solve it. So, and just have it numerically solve it for a particular problem. But this is the way that they would use, like if you're doing theoretical physics and doing something like nuclear physics, for example. This would come in pretty handy.